Hi. I've known Milo here for a really long time, and he was brave enough to come and be our keynote, even though I know enough dirt on him to probably embarrass him several times over, but I'm not going to. Anyway, so I met Milo virtually in 1989 when I was in the Merit NOC, and there was an earthquake in California. And one of the NOC operators happened to be exchanging email with Milo at the time of the earthquake. And Milo said, "Wow, there's an earthquake. It's the biggest shake of my life. I better leave the building now." And I don't think Milo knows this, but at that point, the Ann Arbor News thought that was super cool. They came to the NOC. They put Milo's email on the evening news. And they interviewed our PR person at the NSFNet who said, they asked her why it was that the network was still up when you couldn't make a phone call, and she very sincerely described how the phone lines were actually suspended above the ground, whereas the network was buried, and so therefore it was impervious to earthquakes, which I thought was super duper funny. So the second time I met Milo virtually, we were having a regional text meeting, which is what NANOG used to be. And we were all in this little conference room, and the topic of discussion was how the network was saturated because Milo was playing a war game with his friends. Of course, it wasn't even T1 then. Anyway, so I worked with Milo at Home, which was a really good time, and now Milo is the VP of Access at Google, and I don't want to take any more time from his fabulous talk, so we'll just enjoy. Thanks.
Thank you, Kathy. Wow, it's been a long time since I've been at NANOG. This is a different kind of place. I know maybe 5 or 6 people here. As one of the old guys, I guess Kathy wanted me to come and give a talk about the history of the internet. But to borrow a phrase from Peggy Noonan's book, I think this is more about what I saw at the revolution, and really what the internet, the history of the internet is a story of revolution. I was an early ARPANET user when I was in high school in the Central Valley of California. I actually had an Apple II, and I bought a CAT modem. Any of you remember these acoustic coupler modems? Okay, 300 baud. I heard about the ARPANET from folks at the local university at Fresno State, and I dialed long distance into the tip, right, which was the old name for terminal servers in those days of the ARPANET, and just started exploring. One of the great things about the net back in those days was it wasn't that important to people. Right, so you could actually fool around quite a bit on it, and this was not really frowned upon. There was a computer called MIT-MC where I got my first email account. It ran the Incompatible Time Sharing System, ITS, and one of the funny things was if you tried to log in and you didn't have an account, it would say, "Would you like me to make you an account?" And so that was my first email account. I went to school at UC Berkeley and majored in computer science. And there I learned about Unix. I learned about the ARPANET, and later about TCP/IP. One of the fun things I did was actually get a chance to work on defense programs at Livermore Lab. And I always thought working with nuclear weapons design was always a good background for competing with incumbents. In both places, though, one of the great things was that you got to see computers from different kinds of manufacturers all working together. That wasn't the way most of the world worked back then. I moved to NASA in 1985 and joined a brand new networking group. NASA was mostly a deck shop running VAXs, though at the manned space centers they were IBM mainframe based. So I was the only tech guy in the group. And so what did I do? Well, we ran Unix on VAXs, just like we did at Berkeley. and became an advocate for TCP/IP. And later, my team had the opportunity to build NASA's backbone system. Which brings us up to my first encounter with the IETF. That was in 1986. I was 23 years old at the time. And they were, the great thing about the net back in those days was if you really wanted to advance the internet, you were really welcomed. It's like, another soldier for the fight. Because at the time, the internet was not the dominant protocol. We had SNA and the IBM world, the DEC world, and the internet was anything but a sure thing. The community was tightly knit. This is the attendance list of that first IETF back in 1986 that I attended. I think it was the fourth one. And you could see the usual suspects there, from BBNN, from SRI, the old days of the internet, and 35 people attending an IETF meeting. It's amazing. This group used to be that small a long time ago, and now we're as big as the IETF once was. The status of the net back in 1986. There were 3,082 hosts. You knew that because everybody had to be in the host table. Because the internet hadn't converted over to the DNS at that time. The interesting thing was, 515 total networks, 144 internet gateways, what routers used to be called in those days. We had the ARPANET and the MILNET had just been split apart. These were the old BBN C30s acting as packet switches, and they had the famous 1822 interface by ACC, which was later upgraded to X25, which was a terrible thing. And Craig Partridge and I always used to joke about how we needed to make T-shirts that said 1822 über alles. Now, that's a really inside joke. People know 1822, which was the old protocol that the hosts talked to the imps with. What were we dealing with in 1986? EGP was having problems. There was no BGP back then, and EGP, as folks always had to remind folks, was not a routing protocol, it was a reachability protocol, which worked fine in the days when topology was relatively sparse. But as topology started growing, we had lots of issues. The ARPANET was getting congested. Only 5% of the host pairs on the ARPANET were consuming 50% of the total network capacity. Funny how things don't seem to change. The DNS was still in early stages of the deployment. Many sites still use the old host.txt file. I remember Paul Makapetris, who I later worked with at Home, was there, and he was surprised, actually, that they were getting so many negative hits. That is, people were typing in the wrong name, and it wouldn't resolve. And we also had fuzzballs. The NSS first backbone connected with 56 kilobit links was being turned on. These were small DEC LSI 11 computers acting as routers. David Mills from University of Delaware was the author of that code base, and they were really odd little creatures. Almost as soon as the network became active, it was overloaded. And Dave had to put in the first instance of network management code that I was aware of. He put in prioritization so that telnet traffic and TCP ACKs would get priority over FTP and email. And he had a saying which was, in the jungle, if you want to protect the mice, you have to shoot the elephants. It is interesting that we actually were doing network management and traffic shaping even in this time. Outside of the US, most of the networks ran on the old X25 public data network system, and IP running over that was not optimal. There was a lot of discussion about how to try and finesse this, to try and bring the rest of the world onto the internet. And then we had this thing called the ISO stack. I was actually surprised. The ISO, the International Standards Organization, had a competing protocol at that time. And everybody in the room, pretty much everybody in the room, thought that eventually TCP/IP would be replaced by this thing. It was something that was not really well optimized. It had a connection-less stack and a connection-full stack. And now, like many other technologies, is now on the ash heap of history as the internet ran over it. And we see what's happened since then. There was a conversation with the Internet Network Architecture Committee, who was meeting with the IETF at the time. Blue sky thinking about the future. So I just thought I would put this up. These were considered the mid-range issues and a long-term blue sky vision. Not that anybody would think we could possibly get there. There was a lot of things on the midterm list that didn't actually get done. But on the long-term list, it's really interesting, right? People were talking about scaling the internet to millions, hundreds of millions of endpoints, speeds that would be in the gigabit range, applications accessing the internet at 10 to 100 megabits, issues of security, resource control, how to drive costs down, cellular and mobility were being discussed even back in 1986. And it is a testimony to the vision of the folks who were leading the internet R&D community at that time. Backbone networks then began to be constructed. In 1987, the NSF awarded the second NSF net backbone contract to Merit, IBM, and MCI. And they used IBM PCRT routers. These were RTs running software, running Unix, and acting as routers, stitching regional networks together and supercomputing centers, and that came up in 1988. Initially at my shop, we got the job to build our own backbone to link NASA facilities together. They were initially trunked at 56 kilobits, later via T1s. We used Proteon routers at the time, an old name from history. They were multi-bus based systems, basically small computers, 68,000 computers in a box. And we also carried DECnet around. One of the things that was an issue back in these days was the fight over the protocol wars. You had the Digital Equipment Company corporation pushing its DECnet stack and saying, don't move to TCP/IP. The ISO will come and you just stay on the DECnet path and you will arrive in the international standard. This raised a lot of politics in the agency, and eventually it was decided that we would move both IP and DECnet on a common network platform so we could aggregate the capacity. My friends at Livermore at the Department of Energy began their own IP DECnet backbone effort and deployed it in 1988 as well. Federal networks partnered. One of the great things in those days was even though the internet was effectively run by the U.S. government and the agencies, we partnered with each other so that NASA would use NSF's links, NSF would use our links. One of our favorite projects was there was this crazy guy in Hawaii named Torben Nielsen, and Torben wanted to connect up sites in the Pacific Rim. We struck an agreement with several countries to basically say, look, we'll pull the internet to you if you'll connect our investigators inside your country. And Jeff Houston at ARNet and others remember this, right? Back in the old days, we turned on, I think it was 112 kilobit link to Australia. Was that the 56 at the start? NASA operated that network as part of our agreement. We expressly wanted to encourage countries to build their own infrastructure and created the pipe. It was interesting because in most nations, people didn't really want to talk to each other with the internet. But if you put a pipe into the rest of the world, they'd build connectivity internally to actually get to that, and that worked really well. Over time, costs shifted. More and more costs were borne by the nations, and eventually we could get out of the business. It was a great way to build infrastructure. This is a picture of the NASA network back in 1991. I think at the time we had the highest and lowest latitudes in the network. We had a satellite circuit to a research site at Thule Air Force Base in Greenland, and we also had a satellite circuit to McMurdo Base in the Antarctic. To get to McMurdo was a real problem because, satellites are in geostationary orbit, and so when you're down really south, you can't have good look angle on the spacecraft. We got a good deal on a wobbly satellite who had lost its station-keeping fuel, and so it turned out to be in an orbit that was good. We moved a 9-meter satellite Earth station on an island, Black Island, 40 clicks north of McMurdo Base, assembled it, and then built a microwave relay across the ice cap to McMurdo Base. And that was good enough to get something like half a T1 of internet capacity down there, which was muxed, and they could use it for phone calls, etc. There was a storm at one point which collapsed the roof of the administration building at McMurdo, knocking out the HF shortwave radios that they used to communicate. But the satellite connection stayed up, and so coordinating flights into the Antarctic was done via that link. And later, we actually put a ground station at McMurdo and one at South Pole Station. And there was an old polar orbiting weathersat that had a transponder that was still functioning. And a certain part of the day would pop up over the South Pole, and users at South Pole would uplink data back down to McMurdo Base and get their email and science data moved around. Those were the fun days, when 56 kilobit actually got you something. We had numbers of interconnection issues in these days. In '98, the backbones interconnected with each other in haphazard ways, usually through regional networks. EGP was being used between networks, but protocols like RIP and IGRP didn't do a particularly good job of carrying the external data from one part of the region out to the other, and this was causing a lot of route flapping and other issues that affected reliability. Hans Werner Rahn from Merit and NSF and I were talking about this one night in 1988, and we said, this is stupid. We should just interconnect directly with each other and build points of interconnection. We put a co-located Ethernet concentrator, not even a switch in those days, and we would not route inter-backbone traffic through the regionals anymore. We would just peer with each other directly. We had a building as our telecommunications facility that we used to blow things up in. It was relatively secure. It had something like 12-inch thick concrete walls, and so it was decided that we would be the host for this. We discussed the idea of our bosses, and the next day they gave approval. NSFNet had a T1 hub at Palo Alto, at Barnett, and then they extended an RT up to our site. ESNet and Milnet extended networks, and so we actually had our first real peering interconnect. And the internet was called the FIBA. How many of you here know what FIBA stands for? It's a forward edge of the battle area, right? It's a military term, which is basically the front line. We called it that because we thought it was the front line of routing. And in fact, the Ethernet hub network itself was called the DMZ, or the demilitarized zone, which made sense if you thought of it as the front line of routing. I think this was the first use of the term DMZ back in those days. Later, for political reasons, we had to change the name. Mark Polin, who was the head of the DARPA office that ran the research network, said, I am not going to go in front of Congress and testify about this thing called the FIBA. So change the name. You have to change the name. So we changed it to the Federal Interconnect Exchange, or FIX, and that's how the FIX came about. But the DMZ name still stayed true. We had lots of problems back in those days. The Morris worm in November of '88 erupted. We had lots of Unix machines at Ames, and we were hit with that early. We made the decision to turn off the network interfaces at the NASA field centers. That allowed us to keep control of the backbone, but actually saved a bunch of them from getting infected. 36 hours later, the worm was better understood. I remember that time being on the phone with my friends at Berkeley, who were trying to debug what this thing was doing and how it was doing it. And about 36 hours later, patches were available, and the worst was basically over, though we still had infections at various sites after that. That was I think the death of innocence on the internet, that we would be able to be targeted and affected like that. We also ran a root name server, and like many other root name servers, these were targets for hackers. A number of funny stories that I could tell you about dealing with hackers. We had one instance where there was, at a university in Finland, a guy who kept trying to break into the root. So I called up the folks at the university, and nobody would do anything about it. Eventually, I talked to folks at NordUnet, who wouldn't do anything about it. So I said to my friend Elise Garrick at Merit, hey, could you just put a small route in, route to the null interface for his network? Because that would get their attention, right? And she said, well, we don't really want to do that kind of thing. We don't have a procedure for doing that. Why don't you talk to Sergio Hecker at the John von Neumann Supercomputer Center, because that's where the 112 kilobit circuit to all of Scandinavia came in. So I sent him an email about it. He preferred a more blunt approach. He went into the machine room where the circuit was located and put the link into loopback, turning off connectivity to all of Scandinavia. Needless to say, behavior modification works, and they didn't bother us again. We had another situation where there was a hacker trying to break in, and he was on coming in from an address. It turned out Finger worked in those days. You remember Finger? You could actually see who was logged into the machine and what jobs they were running. And it was clear there was a user on some Apollo workstation at MIT, and he was trying to do this. So I fired up a talk session. I said, hey, stop doing this. This is a U.S. government computer. Don't mess around with it. He, you can't do anything, blah, 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 blah. So then I informed him that all computers that run TCP/IP, because it was a DoD protocol, had a special trapdoor built into them. And if you were to cause a problem, if you didn't stop doing this, I would exercise the trapdoor and take your machine out. And he's, oh, nothing but. Well, the Apollos back in those days had a bug in their kernel. And it turned out it believed ICMP messages from anybody that would send it. And we had a little program that faked ICMP messages. So I sent the machine a ICMP redirect to my address, my host, to his loopback address, and then issued a flood ping. And at that point, the kernel forward the packets at kernel priority and panic the machine. And I was told afterwards that he kept telling people, it's true. There's a trap door in every network implementation out there that the government can control. We also had problems with porn. Back in those days, we had an appropriate use policy, and delivery of porn across the federal networks was not considered in compliance with this. We had to police it because we didn't want to be hauled up to the hill saying, why is taxpayer money going for the distribution of pornography? And have our funding cut off because of that. Also, our international links were modest. In particular, the link to Australia was 112 kilobits, and the Aussies were very good at finding porn on the internet, as it turns out. And the link would redline, and then it was like, oh my God, it's like, how are we going to find this? Fortunately, I don't think people knew about this. The fix at the time was a shared Ethernet, right? So we had a Spark station that was plugged into it, and we would put it into promiscuous mode, it's an Ethernet interface, run TCP dump, and we actually had software that could reassemble the TCP sessions. So we would actually be able to see the FTP requests coming in for the file. And what people would do back in those days is they would find some server somewhere, some host, that had an open FTP server, and they would plug their, they would hide porn in directories named dot, right, and dot, 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 and stuff like this. And so then we would just call up the site, inform them that they were hosting porn, and it would get turned off, and the link would go back down to normal bandwidth. Occasionally, we ran into problems with universities that did not want to, for various reasons, turn it off. So I had a friend of mine at Berkeley who would post on Usenet under the pseudonym Red Meat, and I would have him post the location of the porn on Usenet. Within about 15 minutes, the site was totally barraged with requests, and they would then have to turn it off in order to deal with the network congestion. These were the kinds of problems we had back in the old days. Not that we have them today. Traffic continued to grow, and the T1s became congested. We moved from EGP to BGP, which was a real routing protocol. The backbone networks all had to upgrade, but the costs were high and the equipment was immature. The NSF networks with their awarded an upgrade to ANS, Advanced Network and Services, a nonprofit comprised of Merit, IBM, and MCI, and their DS3-based network came up in 1992. We and the folks at ESNet partnered on a procurement. And we went to go talk to MCI, AT&T, and Sprint, and WorldCom about using either frame relay or ATM as our transport to basically reduce the cost of this. I remember a particularly funny interaction. We went to the AT&T facility in Warren, New Jersey, and that's where the GCNS 2000, the old ATM switch, was being built. And we said, the handler said, the food is here, breakfast is over here, blah, blah, blah. Please don't use the drinking fountains, and then moved on. So I raised my hand. I goes, why not use the drinking fountains? Oh, we have a groundwater contamination problem here. So, and we moved on, and I said, excuse me, but if you have a groundwater contamination problem, why don't you just turn them off? Oh no, they're for the employees to use. Ultimately, after a couple of protests, which are common in government contracting, we contracted with Sprint, and we brought up our own networks. The Fix West and Fix East at the time were upgraded to FDDI to support the load, and the internet really started going. Here's a picture that's relatively famous, showing the traffic growth back from 1988 all the way to 1994 of the NSFnet backbone. As you could see, fuzzballs replaced by T1s, and then eventually by the ANS network. The internet turned commercial. The internet had grown so fast and was supplanting other networks that real companies started getting interested in it. People who work, companies represented in this room. There were several internet operators at the time. Alternet, which was part of UUNet, PSINet, SprintLink had all begun operation. The KIX was formed, the Commercial Internet Exchange was formed in 1991 to allow commercial operators to interconnect. The ANS folks had gotten special permission from the NSF to go ahead and allow commercial use of that system as long as it did not disrupt the main NSFnet system, main NSFnet services. When the government does something that's controversial, people complain, right? And so there were a number of folks who complained, and the NSF, rather than fight all of this, basically said, you know, it's time to get out of this business. So issued a solicitation for network access points, which would allow the regionals to interconnect and allow different backbone operators to then come in attached to the network access points, commercial operators, and transition out of service provided by the federal government. Many of the regional networks at this time were thinking about becoming commercial or doing that themselves. One of the new NAPs in particular was run by Pacific Bell. They used a Newbridge ATM switch. This was just a horrid nightmare. It was a piece of offal. A total disaster. Had huge kinds of packet loss and was a big mess. In 1994, Sean Duran and Andrew Partant from UUNet came to me and said, we want you to open up the federal network exchange point, the FIX, to commercial traffic. Now, just a piece of advice. If your customers ever go to the federal government saying, we want you, the federal government, to do something because we can't get our needs met by your company, this is a big problem, right? So, you know, we hadn't thought about how to do this, but NASA is an odd place, and so one of the things that we have under the Space Act, the enabling legislation for NASA, allowed us to sell time on unique national facilities. This was put in for like launch ranges, launch sites, wind tunnels, et cetera. We would sell time to Boeing to test out new airplanes. So we actually managed to construct a Space Act agreement declaring our telecom facility a unique national asset. And this allowed us to sell access to commercial entities to the facility on a cost recovery basis. So we put up a new FDDI ring. The government networks were dual homed. Commercial networks would then interconnect on the FDDI, and voila, we had a working interconnect. Eventually, lots of people wanted to attach, but our facilities were not big enough to house everyone. So, you know, the May East at the time was operating really well, and so we worked with the folks at MFS to put a bridge link in between our facility at Ames and the MFS hub site in downtown San Jose. And so the big guys were at Moffett, and the little guys would basically connect up at in San Jose at MFS, and eventually both the links were upgraded to, I think, an OC3 at one point with dead giga switches to bridge the traffic, and over time the interconnection moved pretty much all exclusively to MFS in San Jose. Steve's nodding his head. He'll keep me, another old guy here, keeping me honest. So I just wanted to say, at this point, you know, some new technologies came out, and the internet has really been riding on the backs of these technologies for some time. The Netscape was formed after Mosaic was released. I remember, you remember, are those of you old enough to remember when Mosaic first came out? Yeah, so I got a phone call from a friend of mine, I was still at NASA at the time, at Berkeley, and he said, Milo, have you seen this thing, Mosaic? I go, yeah. He says, you've got to stop it. And I'm like, well, Phil, you know, I work for government, but I don't exactly have the power to do that. He goes, you have to stop it. I go, why are you so excited about this? Don't you understand? This thing allows you to use graphics and all kinds of things. Anybody can use it now. And it's inefficient. Because at least with Gopher, you'd get a link and you download the thing. You wouldn't start a download until you actually got the file that you wanted. This thing, you'd be clicking through. Who knows what you could, you know, download. It'll destroy the internet. You have to stop it. And there's a certain amount of truth into that. And that is to say, one of the things that we can do is we can throw bandwidth away or do things that are less efficient from a bandwidth and network perspective to improve user interface and generate a better experience that allows users to get their productivity done in better ways. At Livermore, we used to run the craze in interactive mode, not batch, like many folks did. And even though that was technically not efficient, it was much more productive because you could see a run going south on you. You could abort the job and then and fix it. And this was the same kind of thing. The problem, of course, is this fueled a massive growth in users, devices, and server-based applications. It really allowed the web, right, allowed computing to move from the edge into what was then not called the cloud. But that's the ride that we've been on. Of course, that drives the need for bandwidth. And dial-up networking at the time was really not able to sustain the kind of interface and experience that the new browser systems wanted to be able to provide. The other thing that really saved our bacon was DWDM, right? Cost of photonics and the cost of transport allowed DWDM allowed that to decline very rapidly. And what that meant was you're in a system where traffic was growing, the next increment of capacity that you added to your network was cheaper than the last increment. And as long as the next increment is always cheaper than the last increment, your average cost keeps declining. And so in a system where volume is growing at an astounding rate, if you don't have that dynamic going on, prices have to come up, rationing has to be implemented. But we have ridden this a long, long way. DWDM first started being deployed in the mid-90s and now is extensively deployed even on metro networks. We also had a similar thing going on with Moore's Law and Shugart's Law, basically reducing the cost of CPU, MIPS, and storage. Again, fueling that, right? So that the next increment of compute, the next increment of data center is cheaper than the last. And so the average cost continues to decline even though load continues to grow. Without these two forces controlling cost and the browser empowering new applications to be delivered without having software being distributed, the internet would really not have become what it is today. Of course, the browsers of today are different than the browsers of 1996. When I was at Livermore, we had a saying, I don't know what language I'll be using in 5 years, but it will be called Fortran. And the similar thing is, you know, we still call it a browser, but it's a very different animal than what it was back 25 years ago. For me, I was recruited by John Doerr from a famous venture capital company to go found a new company called At Home. And we were going to go out and build a new network delivering broadband access using the cable infrastructure We use all three of these technologies, DWDM on the backbone, the servers as caches initially, and the browser to really give people the ability to use a broadband connection in new ways to advance the ball. And I think I just want to conclude by saying, you know, all three of these trends have continued. Today, DWDM and photonics continue to deliver more and more capacity at lower cost. We have massive data centers. Certainly, my company, Google, has those. The cost of storage is also declining. It makes it much more cost-effective to put services in the cloud and to push data closer to users. CDNs today actually do what we used to use the caches in the network for, except they're now pushing a volume of data which is truly amazing. And web browsers continue to advance and empower better and better UIs now that you can get high-definition video effectively played back in your browser. I believe as long as these trends continue, the internet is going to continue to scale. But if DWM stops, if Moore's Law stops, we could be in for a world of hurt. Let's hope that the engineers and scientists who work on this continue being innovative and paving the way for new services in the future. So that's all I have. I wanted to, if there's time, we could take a few questions. Questions from the old days.
That doesn't work. Does not scale. And Tom Capella, 5nines Data. Excellent presentation. Thank you. I've seen a little bit of this work, leftovers anyway, at NASA Ames research on various tours, and friends in the computer rooms still are seemingly pretty important for what's going on at the agency.
Yeah.
So some things haven't changed. One thing that also hasn't changed is some QoS stuff. Everyone knows I like QoS. So back in the old days, or the previous days, how much of this QoS interest was in prioritizing control protocols, not just the application layer 3 and stuff higher, but EGP itself or things like that?
You know, one of the most famous failures of the ARPANET occurred because the control traffic was routed at the same priority as data traffic, and basically the control system couldn't converge quickly enough. We have had these kind of problems for some time in the internet. I think, you know, in general, QoS can be used, we see QoS used today by network operators on their internal networks, but we still don't have end-to-end QoS. We don't have the settlement arrangements that can work. This was one of the topics back in the late 80s that everybody was thinking, yeah, we're going to make QoS work, we're going to make it work end-to-end, because ATM did that. And we needed something that would do what ATM did in the internet. Actually, MPLS is now living ATM's dream, if you want to think about it that way. A poor analogy, but we have those kind of switches now that can give us that kind of QoS at the traffic management layer and allowing our networks to scale in ways that ATM was supposed to do, but didn't. Yeah.
Rob Seastrom. I'm at Time Warner Cable these days, but many years ago I was an ankle-biting high school student who inhabited Dave Mills's lab at University of Delaware.
Ah, yes.
And I apologize for asking you a question at the mic, which I probably should ask you in private. But when you brought up Proteon,
Yeah.
I was really hoping that you might say something that would lend credence or rebuttal to the story that I have heard repeated to me a couple of times many years ago about not so easy this time, Milo.
Yes. This is a very old story. I was relatively young in those days and unmarried. I didn't get married till 38. And there was one holiday I think it was Memorial Day, and I was the base was shut down. I didn't go into work, and I was totally bored, and I couldn't figure out what to do. So I started doing a very odd thing. I took the Proteon software executable, the runtime, and I piped it through strings in Unix, which printed out all these ASCII strings in the code. And I noticed there was this funny string that was located next to the word login. And then I said, well, I wonder what. And I tried that, and it was a universal backdoor password. It turned out to work on every Proteon in manufacture. Proteon had put it in for field service access and had figured nobody would ever think to look. And I called them up, and I said, I read them the Riot Act, right? You can't put backdoors into products that you sell. This is like a no-no. You've got to fix this. So they created a variable which would turn it on, right? And so you could disable the field service password. No Chiappa at the time, right, was working for Proteon, and he sent me, there was a new release, and said, Milo, did you try the new release? And I'm like, no, you have to try it. I'm like, fine, we loaded it in the lab. He says, so? I'm like, what do you mean? They had handcrafted in the exact same location in the code, in the executable, the words "not so easy this time, Milo," in the right where the old password stored in the clear was. So this is the kind of fun we had in the old days. One more, that will go. Yeah, Kevin.
Kevin Overman, ESNet. Just wanted to thank you for mentioning some ancient network terminology that has almost disappeared. Things like RIP and EGP, particularly EGP, because there was recently a posting to the NANOG mailer on the discussion of ASNs, and the comment made was, well, ASNs only goes back as far as BGP, because before BGP they were of no use for anybody. They didn't exist before then. And I had to explain, yes, ASNs actually went back far before BGP.
That's
they
right.
were darn useful, even if the protocol wasn't.
Indeed. All right. Thank you for joining me on a little blast from the past. It is good to keep in mind the mistakes and foibles of the past as we move forward in the future together. Thank you.